Welcome back. In this lecture, we will see how to do a damage analysis using a Kenlayer software. So, we have been already introduced to a damage analysis here. A damage analysis is carried out for two different damages on the pavement. One is the fatigue damage that occurs in a HMI layer, and we can say that the tensile strain at the bottom of an asphalt layer induces this fatigue damage, and this is the result of a fatigue damage you can see here. And this second damage analysis is a rutting in a subgrade layer, and we know that the vertical strain at the top of a subgrade layer induces this rutting. So, this is the consequence of a subgrade rutting. You will see the subsequent layer ruts, and you will see something like a permanent deformation on the subgrade layer. So, if you want to analyze this damage or how these damage progresses with the number of repetitions, this damage analysis will be helpful for this. We are familiar with this equations, or DR is a damage ratio, which is nothing but the ratio of a predicted number of load repetitions by allowable number of load repetitions. So, predicted number of load repetitions can be grouped for different class of load. That class can be differentiated based on axial type and load group. And different period can be 1 month or year or any specific period which we are interested in. So, now this Nij, which is in the numerator, is computed from the traffic data, and capital Nij, which is in the denominator, is computed from the structural capacity here. So, the damage ratio can be computed for any given period, and this damage ratio can be used to check how this damage is progressing with different period. So, now let us focus on the denominator value Nij. So, how this Nij is computed is, we need a critical stresses and strain that causes the specific damage, and we know that fatigue damage is caused by a epsilon T, which is a tensile strain at the bottom of an asphalt layer, and epsilon C, which is vertical compressive strain at the top of a subgrade layer, induces rutting in the subgrade layer. So, you have two damage analysis performed simultaneously. One is related to a fatigue damage and other is related to a rutting. So, fatigue damage of HMI layer and rutting of subgrade layer. So, this now this epsilon T has to be related to number of repetitions. So, we have a function here which we are already familiar with. So, NF, which is relating epsilon T to number of repetitions. So, you can see that NF is a function of epsilon T, and you have three different constants here, F1, F2, F3, and even here is a modulus of a layer. So, NF can be computed using this expression. You also know what is these values of F1, F2, F3 for different standards. For example, Asphalt Institute method have different values of F1, F2, F3. IRC have a different values of F1, F2, F3, and these values have been already introduced to you by Professor Neetu Roy. So, now ND, which is nothing but number of repetitions of a standard axle corresponding to epsilon C. So, this ND corresponds to a rutting damage. So, now for any given load value, you can compute epsilon C, and for any given period, you can compute this NF and ND values. So, once you know this value, damage ratio can be computed using this expressions. So, knowing the damage ratio value, inverse of damage ratio gives you the design life of the pavement. So, let us solve this numerical now using a Kenlayer software. So, we have a 3-layered structure. So, the layer consists of 4-inch asphalt layer thickness, 8-inch base thickness, and infinite subgrade thickness. The modulus of the asphalt layer is considered as an elastic modulus, which is 4 into 10 power 5 psi. Base layer is considered as a stress dependent modulus, and it is given as K1, which is 8000, theta power K2, which is 0.5. Subgrade layer is considered as an elastic modulus, which is constant, and it is 10,000 psi. Now, Poisson's ratio values are given as 0.4, 0.3 and 0.45 respectively. You also have a earth pressure constant K0 to be 0.6 for the base layer, So this will be used in computing the gamma self weight of a material and further the modulus values. So gamma value for two different layers are given as 145 and 135 psi, first and second layer. Third layer gamma value we don't need it because we are not interested in finding any of the stress below this depth. So self weight is sufficient up to this point. And you can consider this value to be, third value to be 0 when you solve it. So this structure is subjected to a dual wheel load with a pressure intensity of 75 psi each, and the radius of this given as 4.5 inch, and the center to center spacing between the two wheel is given as 13.5 inch. If this is the case, now what the actual number of repetitions of this load applied is, it is given as 100 per day. So these values are, it's a very minimal value, but we use this value for learning how to compute a damage ratio. If you really wanted to compute for the existing conditions, you can find out what is the number of repetitions of this standard axial load and use the repetitions here. And we will use the Asphalt Institute failure criteria for computation of a damage analysis. It means if we are using Asphalt Institute failure criteria, we have this equations. So the value F1, F2, F3 and F4, F5 constants, we will consider it from the Asphalt Institute failure criteria here. Now determine the life of the payment by a Kenlayer, and we will also find out what should be the number of repetitions of this load for a design life of 20 years. So we will first check whether what is the life of the payment. We will check whether we are getting the life of the payment to be 20 years. If not, if it is less than 20 years, the next question is what is the number of repetitions required for the design life of 20 years. So now when you go to a Kenlayer, you will see first a general option. When you go for open a new file, you will get a general option. In the general option, you can see that type of material, you have a nonlinear analysis. So we give a nonlinear analysis because base course is considered as a pressure dependent material modulus. So it is 2 here. Damage analysis we are going to perform. So in the previous cases we kept this to be 0. Now we are not going to keep it as 0. You can either use 1 or 2 depending on whether results what you need is a summary or a detailed results. So I have kept here as a damage analysis 2. And number of period per year and number of load group here is 1, but these numbers can be different here. So the I here value here, that is this J value here represents number of load group, and I value here represents number of period here. Okay. So if you have other than 1, so this summations to be considered here. Tolerance of numerical integration same as our previous default value, and the number of layer is 3. So base course is considered as a single layer and modulus is determined from the single layer analysis. If you want, you can keep this to be 4 and divide a base course into two different layer and compute the modulus. So I am preferring method 2 here. So I kept the number of layers to be 3. Number of Z coordinate for the analysis. So we need a critical stresses and strain, one at the interface of asphalt layer and the base layer, and second at the interface of base layer and subway layer. So you have 2 here. So other numbers here are as same as previous thing. So once you give this input, the next value is Z coordinate here. Since we are doing a damage analysis, Z coordinate will be selected by default and we don't need to give any number of Z coordinates here. So it is picked. The location is at the bottom of an asphalt layer corresponds to fatigue damage analysis, and at the top of a subgrade layer corresponds to rutting analysis, and we cannot change the Z coordinate here if you perform a damage analysis. Now coming to the layer input, you have first layer of 4 inch thickness, second layer of 8 inch thickness, Poisson's ratio first layer is 0.4, second layer is 0.3 and third layer is 0.45. Gamma value was 145 for first layer, second layer is 135 and third layer I am just assuming it to be 0, that is weightless. Okay. Now when you go to a moduli input, since we have given only one period, you will have a moduli for only one period moduli, but you can define as many as 12 I's here for 1 year. So your I value here can be maximum of 12. So you see for 3 different layers. First modulus is 4 into 10 power 5 psi. Second modulus is a seed value which is assumed here because it's a stress dependent modulus, and third value is also an elastic modulus of 10,000 psi. So the same value is given here as an input. So once the moduli is done, the next one is load group. So as similar to the modulus value, load group can also be of many number of category. Here we have only one load group, so it is a single axial dual wheel. It is defined as load category 1. Contact radius is 4.5 inch, contact pressure is 75 psi. The center to center distance between two wheel is 13.5, and it's only one axial, so XW is 0. So now let us give number of radial contact point as 3, and when you double click on this 3, you have to define what exactly the 3 point is. I have used 0, 0, which is exactly at the center of one load as point 1, 4.5 is at this point, and 6.5 is at the middle of the loading. So we cannot define Z point, but you can fix the radial point here and determine which point the stress value is critical. So once the load input is given, the next input is nonlinear analysis input. So in the nonlinear analysis input for general, so number of layer for a nonlinear analysis is 1. Keep in mind the nonlinear analysis in Kenlayer represents the stress dependent modulus value analysis. Number of iterations and other things as explained in the previous case, I just kept it as a default value. So now the next input is a non-seasonal input which defines which layer has whether it is a granular layer or a soil layer. So second layer is considered as a non-linear layer, and the depth exactly what we wanted to do the nonlinear analysis is upper quarter point of the base layer. So 4 plus 2, which is 6 inch thickness from 6 inch depth. This is a granular layer, so you give n clay to be 0, and this granular layer the default value of a K2 value is 0.5 and the coefficient of earth pressure is 0.6, which is given in the question itself. Now the next input is a seasonal input. So this seasonal input, again this is a value of K1 which we are going to give it to be a seasonal. So it varies with the number of period which we define. Here we have defined only one number of period. So for a seasonal input, you give the value of K1. K1 here I have used as per the question, it is 8000 psi. So we restrict the K1 minimum value here. So pi is taken as 8000 psi here. So now if once the nonlinear input is given, the next input is a damage input. So in the damage input, when you click on this damage input, you will have 3 options: bottom tension, top compression and volume of traffic. So in a bottom tension, so you have which layer, number of layers you need to do analysis. So this is first layer, layer 1, and F1, F2 constants, F1, F2 and F3 constants. So these are the default constant as per Asphalt Institute method. If you have any other constant other than this, you can edit these numbers. So these numbers are used for computing a damage ratio based on fatigue damage analysis. And the second one is a top compression, which is at the top of a subgrade layer. So it's a third layer and third layer. So you have F4 and F5 constant. So these constants are based on an Asphalt Institute method. You can edit these constants value if needed. The next input is for a damage analysis. So when you click on this damage analysis, you will get this load repetitions for each period. So we have defined only one period here. So for a duration of 1 year. So now you compute what is the number of repetitions of that specific load group. In equation it is given that 100 axial repetitions per day. So if you multiply by 365, you will get 36500 per year. So this is going to be a number of repetitions of this particular load group in 1 year. So this is the result after compilations. You can see the first result to be the computation of a base layer modulus. So, initial modulus what we assumed is 10 power 4 psi. From the initial modulus, we compute the stress value. From the calculated stress, it will recompute the modulus value, and this process was iterated 7 times so that the results to converge, and final modulus of a base layer is 2.958 E4 psi value. So, this modulus was obtained for the 3 normal stresses as indicated here. You can see that out of 3 normal stresses, 2 normal stresses have a negative value. So, the catch here is, in a previous analysis what we did, this normal stress was adjusted to 0, but here it is taken as the same negative value without any adjustment. This is because we have used a pi I value to be equal to K1, which is equal to 8000 psi. So, we have defined a minimum value here. So, there is no adjustment of a normal stress to 0, negative normal stress to 0. In case if we used pi value to be 0, as we have not defined any minimum value here, this stress value will have been adjusted to 0 and the modulus computed will be based on this adjusted stress. So, for the computed modulus, the critical stresses and strains are determined. So, for the strain that induces fatigue damage is minus 2.799 E minus 4. So, it is a tensile strain, and from this tensile strain the damage ratio will be computed, and the computed damage ratio was found to be 5.654 E minus 2. And the critical stresses that induce rutting in the asphalt layer is 6.850 into E minus 4, that is at depth of 12.0001 inches, and this induces the damage ratio of 1.822 E minus 1. So, now you have 2 damage ratio, one is for a fatigue damage and other is for a rutting. So, now whichever is the maximum is considered to be the critical damage ratio. So, damage ratio corresponding to rutting here is considered as a critical value. So, now if you want to find what is the design life of the pavement, the design life of the pavement is based on the critical damage ratio. Here in this case it is rutting. So, you see that design life computed from the damage ratio of 1.822 E minus 1 comes out to be 5.49. So, we see that design life is less than 20 years. If you want to bring this design life to 20 years, we need to reduce the number of repetitions to traffic load. So, now what should be the number of repetitions so as to bring the design life to 20 years? This we have to do it only by trials. So, all other input parameters remaining the same, I just changed the number of repetitions to traffic load per year to 10,000. Just we need to decide this number only by trials. For initial trial, I kept it to be 10,000. So, when you keep it to be 10,000, the damage ratio value computed was found to be 0.01549 and 0.04990. So, you see that the second value is a critical here. From this computed damage ratio, when you compute the design life was computed to be 20.04 years. So, for bringing a design life to 20.05 years, per year traffic will be 10,000 vehicles. So, per day it will be 10,000 divided by 365, this comes out to be 27.4 axial repetitions. So, to extend your design life to 20 years, the number of repetitions allowed is only 27.4 axials. So, keep in mind this is not number of vehicles, this is number of axial here. So, you will also get a design output in terms of a graphical representations in a KenPave. So, this is a graphical representation output. So, let us summarize a Kenlayer analysis altogether. So, we gave an input at different category. So, in the first category is a general input where we defined a title, material characteristics analysis, whether we do a elastic analysis, linear analysis, non-linear analysis, or whether we do a damage analysis or not is defined in the general. Number of period, number of load groups, number of repetitions, tolerance for integrations, all are defined in the general input. So, we also gave Z coordinate. This ZC indicates at the locations where we need stresses and strain. So, it defines a depth. So, we define a layer thickness, Poisson's ratio and a gamma value for determining stresses and strain, and we assume that layer interface to be a default value, and we used a modulus value. This modulus value, if it is elastic modulus, we keep it as constant. If it is assumed as a non-linear, the modulus value is going to depend on the stress. So, for repetition, for determination of a modulus value at a particular depth, we define whether it is a granular layer or a clayey layer. If it is a granular layer, we give a modulus to be a function of k1 theta to the power k2, and if it is a clayey layer, we assume a two slope function, and from the two slope function we determine the modulus value. So, you can also account into consideration the seasonal variations in all these analysis by defining number of periods. So, you can maximum define 12 number of periods for computation of stresses and strain. And we did not do any viscoelastic analysis, and this viscoelastic analysis corresponds to the analysis of a HMA layer, and this is out of scope here. And we also performed a damage analysis, and we computed a design life of a payment based on the damage analysis. So, for doing a damage analysis, we considered two damages. One is fatigue damage of a HMA layer, and the second one is rutting at the subgrade layer. And for performing a damage analysis, you need to define constants here, F1, F2, F3 for a fatigue damage analysis, and these constants are editable. You can either use an IRC constant or Asphalt Institute or any other constant obtained from the laboratory test. You need F4 and F5 constants for a rutting analysis, damage analysis. So, in addition to this, to compute a number of repetitions of a traffic load, you also need a volume of traffic. So, from these parameters, you compute the damage ratio value, and the inverse of damage ratio value will give you the design life. So, this is what we have seen in the Kenlayer analysis. Thank you so much for your patience, and we will get back to you with the IRC design. Thank you so much.